welcome. We are discussing about measurement of resistance, and we have said that measurement of low and high value resistance needs special care. For example, we have seen that if the value of a resistance is small, then the contact resistance or the terminal resistance that becomes comparable or significant in comparison to the actual resistance itself. Therefore, we need to take care of how to avoid contact resistance or any problem due to contact resistance or terminal resistance. Today in this video, in this class, we are going to see what are the problems that we may encounter when we are measuring a high resistance. Okay. So, high means very high, it could be several mega ohms or even higher, and a particular example of this is measurement of insulation resistance. Okay. So, insulators means non-conductors. So, they ideally should have infinite resistivity or zero conductivity, but nothing is an ideal insulator. So, they have some conductance or they have a very high resistance, but that is not infinite, that is high, but not infinite. Now, suppose I have a block of insulating material. Okay. So, say I have a rectangular block of insulating material which is like this. Okay. Now, what I will do, I will put two conducting plates on two sides of this block, maybe one conducting plate here so this is a conducting plate on this side, and similarly we will have another conducting plate on the other side, which is here. Okay. So, let me erase this. Okay. Now, so this is insulator and this is conductor, maybe copper. Okay. So, say this is copper and this is some insulator. Now, what we will do, we can connect these two plates to a voltage source like this. A sufficiently high voltage source, otherwise the current, almost no current will flow through this insulator, because this is an insulator, but not a perfect insulator. So, if you apply some voltage source through it, then some current will leak through the insulator. Okay. So, there will be some leakage current through this insulator. Now, if say the cross section area of this insulator is A. So, this area, cross section area, okay, and say this length through which current flows is L, Okay, and if the insulator has a resistivity of rho, so this is resistivity which should be very high for an insulator, then we know the resistance offered by this block is given by R is equal to rho L by A. Okay. And the current flows through the entire volume of this insulator. Okay. So, the charge or the electrons, they flow through the entire volume, means if this is the 3D volume of the insulator, then the electrons will flow through it everywhere through it. Okay. So, sorry, this is, if it is electron, then I should draw it in the other direction, minus to plus, and it flows everywhere inside, okay, inside the volume. Okay. And so if you see from this side, okay, from here, if you see from here, you will see then this cross section as a square, and you can see the electrons moving through the volume everywhere. Okay. It will fill the entire volume, and this conductance of the current you can call the volume conductance. Similarly, this resistivity we call it volume resistive. This is volume resistance, and this we call the volume resistivity. Okay. So, R is said the volume resistance and rho is said the volume resistivity. Okay. So, the dimension of rho will be, so its dimension will be ohm into say meter square divided by meter. Okay. So, its dimension will be ohm meter. Okay. Now, there is also some current which will flow only through the surface of this insulator. Okay. So, there will be also some current or electrons which will flow only through the surface. Okay. So, that means only how do I draw it? So, just consider this surface, okay, which is the periphery of this block. So, from there we will also have some electrons flowing only through the surface. Okay. So, if you look from here, you will see this electrons only at this surface, okay, only on this line. Okay. So, this particular type of conductance where current flows only through the surface and not through the volume is called surface conductance, and the associated resistance to that we call it surface resistance. Okay. So, we let me use a V symbol. This is for volume, V. So, this is volume resistivity and this is surface volume resistance and volume resistivity. Similarly, we can define a surface resistance which will be proportional to some constant which we call the surface resistivity multiplied by the same length, but divided by the periphery the peripheral length of this this block. Okay. So, call that what can I call, periphery, say small p, okay, where this periphery is this length. From here up to this, then you go like this, then you go like this and like this. So, this is the periphery p. Okay. And also if you call, say, this distance as w and this distance as h. Okay. So, this is the height, this is the width of the block, then this p periphery, then p periphery is equal to 2w plus h. Okay. This is what is called the surface resistivity. Rs is surface resistivity, and rho s is, sorry, this is surface resistance, and this is surface resistivity. Okay. So, the important difference is that for this phenomena, electron flows only through the boundary or the surface of this material, and for this phenomena electron flows through the entire volume inside of the material. Now, the physics of these two conductance we are not going to talk about. So, that is beyond our scope. So, we will only stay happy here by knowing this fact that some current flows through the volume and the resistance offered to that current is called the volume resistance, and some current which flows only through the surface is associated with what is called the surface resistance and surface resistivity. And the relationship is quite similar. Here we see that this resistance, volume resistance, is proportional to the length of this block. That means how long the current should flow. It is inversely proportional to how much area or how big, how wide the path of this current is. The thicker, the bigger the path, the resistance will be smaller, and the proportionality constant is called surface volume resistivity. Similarly, here this resistance is again proportional to the length, how long the current has to flow, and is inversely proportional to how big the periphery is, how wide the path of the current is, which is this peripheral length. Okay. And the proportionality constant. So, this is a constant which is called surface resistivity. Okay. Now, the fact is that normally we ignore the surface conductivity or surface resistance, okay, and we assume that this surface resistance is very high. Here, I mean, as high as infinite. Okay, nothing is infinite. So, by this I mean it is very high. Okay, and therefore, we generally ignore this. Okay. So, if this block was a better conductor, then almost the entire current will flow through the volume and very little amount of current will flow through this surface. So, therefore, we ignore this surface conductance. But when this itself is an insulator, so that only a small amount of current goes through the inside, through the volume of this block, then this surface current is also comparable to the volume current. Okay. But for insulators, since the volume current itself is very small, thus the surface current, which is also small, but now it becomes comparable, that means no longer negligible, comparable to the volume current. Okay. So, if we want to find out so if this voltage is V, and if we want to find out how much current will flow through this block. Okay. Now, these conductors will have very little resistance, so that you can ignore. So, this current I will now be given by I is equal to let me write it here, this I will be equal to V, this voltage, divided by the resistance offered to this current. But now there are two parallel paths, one path is through the volume, another path is through the surface. Okay. So, here we will have R V parallel R S. Okay. So, we have two paths for the current to flow, and the two phenomena is different, but the physical phenomena we will not discuss. We will stay happy with the fact that okay, there are two types of current, one flows through the surface, one through the volume. Okay. So, this is what I will highlight. Not plus, they are not in series, sorry, this is a mistake, they are in parallel. Okay. And if say this R V is much smaller than R S, then this quantity will be equal to I equal to V by R V only, because if R V is much smaller than R S, then this parallel combination will be same as R V only. So, if this is true, then we can write I is equal to V divided by R V only, and we can ignore R S. Ignore means we assume it to be very high or infinite, not 0, it is very high. Okay. So, approximately. So, this is normally what we do, we never talk about R S, surface resistance, but here we have to talk about surface resistance, because R V itself is very high, So, what we have seen is that while measuring high resistance like insulation resistance, there may be a parallel surface resistance which may affect the affect the measurement. Okay, so this is what we have seen. Okay. Now, let us see a practical scenario, let us take a practical example where this will be more clear. Suppose we have a coaxial cable. What is a coaxial cable? A coaxial cable looks like this. So, it has a central core, a cylindrical core which is of course some metal, maybe copper. Okay. So, it has a core and surrounding this we have a layer of insulator. Okay. So, surrounding this we will have a layer of insulator, like this, and then surrounding this insulator we will have another layer which is again a metal, copper, aluminum or something. Okay. So, after that we will have another layer on top of it, which is again a conductor. Okay. So, this is a conductor, the outer one is a conductor, the inner one, this is also conductor, and the middle one is insulator, this is insulator. Okay. Although I have drawn a small or very short coaxial cable, but this cable in principle can be very long, and this is the cable which is often used for power supply, underground power supply in many of our houses often. Okay. So, maybe it is possible that this inner core acts like the live phase, or say the positive terminal, you can think of say positive terminal of a power supply, and the outer one is the ground terminal or the neutral phase. So, this way we can have a long, very long power carrying coaxial cable. You may have seen some similar coaxial cable in your if you have a cable line or a DTH line or anything, your television. So, in your television the cable that carries signal also is a coaxial cable, okay, which has a central core and the outer metal sheath, and there is some insulator between this. Now, the insulation between this should be able to separate these two conductors perfectly. There should be no leakage current between the inner core and the outer sheath, but no insulator is perfect. So, we may be interested in finding out how good this insulator is. That means, we would like to find out the resistance offered by this insulator. So, for that what we will do? We will once again connect say these two conductors. So, this one and this one. So, these two are conductors, the core and the outer sheath. We will connect this to a battery, and we would like to measure the current that flows in this circuit. Okay. So, we will put say an ammeter. Okay. So, let us put an ammeter. Okay. So, now if we know this voltage, if we get some reading I, then we may like to find out the R as V by I. So, this is the resistance between this this central core and this outer sheath. Okay. But if we do in this way, we will have a small problem. What is that? Let us see. Before that, let us first find out the path of the current that flows. Okay. So, path of the current. So, current comes from or say electron comes from here, it comes here and then it gets distributed all over this orange color conductor. Okay. So, electrons come here and then these electrons go through the insulator to the central core. Okay. So, the electrons flow like this from this side as well as from this side everywhere. Okay. So, if we see from the front, okay, so the front view, in the front view we shall see that this is my insulator, then we have this central core and outside we have this sheath. Okay. So, the front, this is the front view. So, we shall see electrons flowing like this radially everywhere from the outer sheath to the inner core. Okay. So, this is how the electrons flows. This is one path for the electron to flow from here minus terminal to the plus terminal. But there is another path which is only through this surface or boundary of this insulator. So, electrons can flow only like this, only through this surface, okay, not through the volume. Okay. So, this is only through this conical, okay, part of this insulator. Okay. And these electrons do not flow through the volume of the insulator. So, this is the surface current and this blue one, this is the volume current, and these two currents are flowing into parallel paths, right. So, both are starting from this outer sheath and ending at this central core. So, these two currents are parallel, okay, and these two resistances offered to these two currents, we can call them as R V, volume resistance, and here any resistance offered to this we call it as R S. Okay. Okay. Now, we may have actually another surface area, open area on the back side of this long cable. Okay, we can see only the front side from this drawing, but there is definitely some the back side will also have this this open or exposed area of the insulator. So, we will also have some surface current there. Okay. So, this is the back side of this insulator. Okay. So, basically we have like R S here, and you can think that, okay, there is another R S, call this R S 1 and they call this as R S 2. Okay. So, we have R S 1, then R V and R S 2 in parallel. Okay. So, if we draw a side view, so let me try to draw a side view. So, this is the central core, then we have this insulator. So, this is very long, I am drawing it small, but this is actually very long, and then another metal. Okay. And then we have the surface current flowing only here, here, here and here. So, this is the surface current, So, this is side view as we are seeing from this, and the volume current flows here. Okay. So, this is the volume current, or current is in the opposite direction, this is the direction of the electrons. Okay. So, volume currents flows everywhere, surface current flows only through the surface. Okay. So, these three are in parallel. Now, say we want to know so say we have say 1 kilometer long coaxial cable. Okay. So, question, so you have a 1 kilometer long coaxial cable, and we want to know the resistance between the central core and the outer sheath outer conductor for this long cable, for this 1 kilometer long cable. But suppose we cannot. So, what we have to do to find this answer? We have to perform this experiment. We have to apply some voltage and measure this current. But we cannot do this experiment suppose with a 1 kilometer long cable, because that will be a huge arrangement. So, maybe we are doing this experiment with say 10 meter long cable, or maybe 1 meter long cable. Okay. So, we cannot perform the experiment with 1 kilometer long cable. So, we perform with say 10 meter cable. Okay. So, we have this cable 10 meter long. So, you have this 10 meter long cable with this insulator and this sheath. So, this is 10 meter. Okay, and we are applying a voltage between this and this. Okay, say we have a voltage applied like this, and we are measuring this current with an ammeter. Say this voltage is found to be we know this voltage is or we can measure this voltage. So, this is 1 kilovolt, and say this current is found to be 1 microampere. The length of this conductor is 10 meter. Okay. Now, if we do the same experiment with had we done the same experiment with 1 kilometer long cable. Okay. So, this is 1 kilometer. If we had done the same experiment with this same voltage 1 kV we apply and we measure the current. Okay. So, this current I, so what do you think this current I will be? Okay. How much will this current be? Roughly speaking, this I should be, so this is 10 meter, this is 1000 meter, so this is 100 times longer. Okay. So, we have 100 times more path for the electrons to flow. Here this is the path for the electrons mainly, and here we have 100 times longer path. So, definitely I, this current I will be expected to be around 100 times this current, which is 1 microampere, right, because now we have more current. So, for this cable, therefore, we could have estimated the resistance like as this voltage 1 kV divided by 100 times 1 microampere for this experiment. Okay. So, with this experiment is not performed, this experiment is performed, and from this we are trying to guess what would have been the value of this current if we actually had 1 kilometer long cable. But this result is not correct. This result is not correct. Why it is not correct? Let us see in detail. So, in this experiment, okay, so this with 10 meter cable, the current that we have I, this is given by the voltage V. So, this is V divided by the total resistance, and the total resistance is the parallel combination of the surface resistance and the volume resistance. Now, this we can write as the surface resistance plus parallel R V for this experiment. Okay. And therefore, you can also write this as say V multiplied by, so R is resistance. So, let me call C for conductance, Cs is surface conductance, which is same as 1 by R s, and Cv as volume conductance, which is 1 by R v. Okay. So, then this we can write as V multiplied by Cs plus Cv. This is for this experiment, and similarly for this experiment we can write I as once again V multiplied by Cs plus Cv. But now, so let us call this Cv as Cv 10. 10 means 10 meter conductance for 10 meter cable, and let me call this as Cv 1000. Okay. So, now we can write that this is approximately, we can expect that this will be Cs plus 100 times Cv 10. This is Cv 10, this is Cv 1000, this will be 100 times of this, because now we have 100 times more path for the current to flow. Okay. So, I will be this, and you see this is not equal to, so this is called, they call this I 10 and this is I 1000. Okay. So, I 10 is 1 microampere and I 1000 is this. This quantities you see is not equal to 1000 times I 10. Okay. Because Cs is not equal to 0. If Cs was 0, if we had if we say erase this Cs, if we can forget this Cs from here and here, then you see these two currents are like 100 times of each other, not 1000, 100. Okay. So, but because of this Cs, it will not be this will not be 100 times of this, and then this Cs you can possibly expect to be of same value, because here also the surface, these two surfaces are almost similar to these two surfaces. So, Cs here and Cs here may be same. Okay. So, we may write Cs for 10 meter should be equal to Cs for 1000 meter. Okay. So, now therefore, if we perform the experiment with a smaller cable, we cannot multiply the current with a factor of 100 and predict the current in this experiment, because of this surface conductance or surface current. So, this is the problem. Okay. So, this is the problem due to surface conductance. Now, let us see this solution. Okay. So, that was the problem, why surface conductance is so crucial to take care. Now, let us see this solution, how to take care of surface resistance. Solution, how to take care of surface conductance. Okay. So, what we will do, we will connect a voltage source between this okay, and we have to measure the current. The solution is very simple actually. So, we have an ammeter. Now, what we will do is this. Okay. So, let us take some copper conductor. Okay. What we will do? We will wrap some turns of a conductor touching this insulator. So, some turns like this. Okay. So, and then we will take these turns and connect it like this. So, now what happens? Say this electrons or current which is flowing from here, it comes up to this, and then it has two paths, one through the volume, another through the surface. So, the part that goes through this volume will come to the central core and has to then go through this violet colored conductor through this ammeter and return. Okay. But the electrons that flow through this surface, after reaching halfway through this surface, they will find this conductor which is of much lower resistance than this surface, and therefore, these electrons will bypass like this. Okay. So, then they will come through this conductor. So, this is a conductor, okay, somewhere. So, these electrons will then bypass through this conductor, they will not go through the ammeter, they will go directly like this and will return the battery. Okay. Similarly, if you have another exposed surface here, then we need another cable, not cable, conductor, okay, which is twisted surrounding this insulator, touching this insulator, in contact with this insulator, but it is not in contact with this core. Okay, this should not touch the core. It is touching the insulator, but it is not touching the core. Okay, and then also we can have another bypass path from here like this. So, this electrons also which were going like this, they will get bypassed and they will come directly like this. So, this current will not flow through the ammeter. So, the current that will flow through the ammeter is only the volume current, which I am calling as IV, and the current that will get bypassed, okay, this is this IS, surface current. Okay, so, this is IS 1, this is called this IS 2. So, this is the total surface current IS, and this current is I, which is equal to IV plus IS. Okay. Now, what is IV? So, we can further write it as IV is nothing but V, this voltage, divided by the volume resistance RV, plus, and IS is nothing but volume, this voltage divided by the surface resistance. Okay. These two surface resistances here and here. So, you can write it like this. If you have two surfaces, you can write them like this, or you can write them as a common surface resistance. So, these two together is RS. Okay. So, this is IS, this is IV, and now this current, surface current, gets bypassed. This wire we call as a guard wire, which lets this surface current bypass through a easier path than this surface. So, they will not flow through the ammeter. So, the ammeter reading now will give the ammeter reading gives IV only. Okay. Now, if we disconnect the these guard wires, okay, suppose we can disconnect it, say suppose there are switches, so that we can disconnect this. Here also we can have a switch, so that this is we can disconnect it. So, if we disconnect it, then the ammeter will give both IS and IV if we disconnect the guard wire. Okay, and ammeter reading gives IV only if guard wire is present. So, therefore, now what we can do, suppose, so we will go back to the previous question. We need to estimate the resistance for a 1 kilometer long cable, but we are doing the experiment with 10 meter cable. So, how can we estimate the result for 1 kilometer cable? So, now say when we have 10 meter cable, okay, we can measure IV using guard wire, and then measure IS plus IV with after removing the guard wire. So, without the guard wire, okay, call this I, and then we can find the value of IS like this. So, I is known, this IV is known as given by this ammeter, okay, with the when the guard wire is present or not present. So, from this we can find the IS. Then we can predict the result for 1 kilometer long cable as so this is IS this is IS 10 meter, IS 10, IV 10, 10 meter, 10 meter, and this is I 10 experiment for 10 meter. Okay. So, then we can predict the result for 1 kilometer cable as IS 1000 will be almost same as IS 10, okay, and IV 1000 will be 100 times IV 10. Okay. So, and I 1000 will be IS 1000 plus IV 1000. So, we can predict the current that would have been flown in an 1 kilometer long cable more accurately, considering this surface resistance or surface conductance. If we did not do that, our result would have been erroneous. Okay. So, this is the important thing I wanted to convey to you, is the fact that while measuring a high resistance, the parallel path, that means the surface resistance, comes in picture, and if we do not consider that, if we do not take care of that, our estimations can be wrong. Okay. So, thank you.